Hello, welcome to the LexHub tutorial on Open Vocabulary Language Analysis, the concept. In this tutorial we will cover the idea of open vocabulary analysis, what it is and why it is important. We will also be posting a tutorial on how to run language analysis tools performing some of the open vocabulary techniques covered in this talk. To begin with, why do we care about language analysis? Well, this tutorial is geared with those who care about language analysis because it reveals who we are. Our thoughts, feelings, behaviors, personalities, beliefs, socioeconomics, culture. One of the reasons language analyses seem to be gaining increased interest in the social sciences for measuring these things is the emergence of social media. This includes websites like Facebook and Twitter, Instagram, WeChat, a growing number of sites. Some say these are the largest accessible data sets in existence of who we are, a window into our daily lives. In this tutorial, we'll be using analyses over social media as an example, but it's important to note these techniques can be used over any medium, though larger is often better for open vocabulary techniques. So, let's talk about how language analysis for social science generally works. One starts with a set of language, such as Facebook or Twitter, including status updates in the case of Facebook or tweets in the case of Twitter. Often one also has a set of outcomes. These could be questionnaire results, one's demographics, cognitive assessments, or even health. These outcomes and the tweets or any text are fed into the language analysis, which is usually focused on one of two applications: prediction or insight. In prediction, one is trying to accurately map language into a single or a few given outcomes. The question for researchers developing these techniques is often, given the language, how well can I measure outcome X? For example, that outcome could be a factor of the Big Five personality construct. My colleague Gregory Park explores the predictive accuracy of language over the Big Five, including factors of openness to experience, conscientiousness, extroversion, agreeableness, and neuroticism. Essentially, one takes the language and produces 5 scores that correspond to each of the 5 factors based on patterns seen in the language. Here we see the accuracy of those scores as compared to questionnaire-based assessment. For example, extroversion has a score of 0.43, which is much in line with what's considered a strong correlation for any behavior with a psychological outcome. One can then run it through other tests of validity, such as comparing that with accuracy of fringe judgments of personality, to get an idea of how accurate it is. And if they are happy with it, they can apply it to new sets of people in place of or to supplement a questionnaire. Another popular example of prediction is screening for mental health. Here we see the results from Coppersmith, Dredz, and Harmon's work on classifying Twitter users for whether they ever mention a diagnosis of bipolar disorder, depression, post-traumatic stress disorder, or seasonal affective disorder. Essentially, when they tuned their model to have a false alarm rate of 0.2, they found their model to correctly identify 82% of people with bipolar disorder. As you can tell, a lot of these approaches focused on prediction are concerned with getting an accurate model to be able to accurately assess people. While prediction focuses on using language to measure an outcome, on the other hand, insight is conceptually focused on the opposite, finding the language that is most characteristic of an outcome. For example, here we see the words and phrases most distinguishing of conscientious people. The size of the word corresponds to its correlation strength, controlled for age and gender. Conscientiousness is characterized as being organized, dutiful, and a preference for planning. Often such people are thought of as good workers or very focused. And we see language reflecting that characterization. Ready for example, busy, to work. However, we also see vacation, relaxing, weekend, suggesting an insight that conscientious people are also more thoughtful about their downtime or about having a balanced life. Another example of insights looks at clusters of related words rather than individual words. Here, my colleague Johannes Eichstadt has found clusters of words related to hate and interpersonal tension as predictive of areas with higher atherosclerotic heart disease mortality at the county level. On the other side, clusters of words which he has characterized as optimism are related to lower rates of mortality. We call these insight applications, where the goal isn't a measure of an outcome, so to speak, but the language patterns that speak to the thoughts, behaviors, psychology, or health of people. So that gives us an idea of why and what one can use language analysis for. However, we haven't identified what constitutes an open vocabulary analysis. In fact, all of the example analyses shown so far use an open vocabulary approach. An open vocabulary approach is characterized as one that does not rely on preconceived notions of what language belongs to a given category. None of these words and phrases were manually selected that correspond with conscientiousness. Similarly, these clusters of words also emerge from the data. Social scientific theory is useful to interpret them, but the analyses are mostly agnostic to theory. In other words, open vocabulary analyses let the data tell the story. To better understand, let's zoom in to what is happening in the language analysis. Here we have a view to language analysis where we have someone's data, including their language, such as their social media status updates or tweets, and some outcomes, such as their personality or maybe assessments of health. Then there are two steps, linguistic feature extraction and statistical analysis. Feature extraction is the process of turning language into variables. For example, if one was analyzing the following sentence, they could create a feature counting how often the is mentioned. Turns out to be 2 times, and you'd probably want to divide that by the total number of words mentioned. Counting the period as a word, this makes a probability, 2 out of 8, or 0.25, or 25% of the words in the sentence are the. In practice, when one is dealing with thousands of words from one person, the percentages end up being much smaller. For example, in some of our Facebook data, the is on average used only 2.5% of the time. Happy is used 0.2% of the time. And football is used 0.05% of the time, or roughly just 5 out of every 10,000 words. This may seem like smaller values than researchers deal with for other variables, but they can often be treated very similarly. In fact, they have a distribution and vary from one person to the next, so one can run statistics across them, just like you would to run statistics across questionnaire data, for example. We will talk about those statistical analyses last. For now, let's talk about some different types of linguistic features one can extract. In addition to simply words, here we've laid out a few features along a continuum from the more hand-driven, or those requiring human judgments of language, to the more data-driven, which use less and less human judgment and rely more and more on statistical analyses over the data to let the patterns emerge. So let's work our way through examples from the hand-driven to the more data-driven. An example of a very common hand-driven approach is manual dictionaries. This approach, popularized by Jamie Pennybaker's linguistic inquiry and word count approach, simply counts how often words appear in pre-chosen dictionaries or lexicons. For example, a positive emotions dictionary might contain the words happy, joy, play, great, etc. One then simply counts how frequent a word in this lexicon occurs in a given text by a person or maybe in a document, and then you'd usually divide it by the total number of words, just like we did with our example with the word the. If you do this for a few people or documents, then you can compare these relative frequencies or percentages across them. Next, let's consider crowdsourced dictionaries. Crowdsourced dictionaries are very similar, except instead of relying on a single or a few experts to decide what words belong in a given category, one crowdsources them from, for example, the service Mechanical Turk or other crowdsourcing services, which allows one to have more of a general sense of how people judged words and less biases from people's own background. For example, because I'm a little biased towards statistics, that ended up in my positive emotions lexicon. That should probably be crossed out if we were to survey people, a wide variety of people. Another approach is using derived dictionaries. These are where you might have annotated messages, for example, of positive emotions, and one learns from these messages annotated with with emotions, what words belong or do not belong in the given category. And so, for example, the word play, it turns out, even though it seems like it's a positive word, is often used with different parts of speech in different senses. You could be talking about playing an instructional video, going to the play, or playing an instrument, or even as a verb, I got played. And it turns out if you annotate a random set of messages, you find out that many of them do not use play in the fashion you expected, and it probably doesn't belong in the category. Similar with great, which tends to more often refer to something being large rather than just something being positive. Another thing to note with derived dictionaries, and often crowdsourced dictionaries, is you can attach a weight to the words. There's no reason every word should be created equal, and so here we see maybe happy has a score of 0.5, while joy has carries a little more positive emotion words of 0.6, and this is all dependent on how whole messages were annotated, how words in their context were annotated. If you think about it, people communicate with each other in sentences, not just simply words, but words always carry context. And so by taking this approach of annotating, using annotated sentences rather than annotating individual words, allows one to take advantage of really how words are more naturally distributed. Another approach that also gives us clusters of words is topics. Topics are automatically derived clusters of words that are often semantically similar, or similar in meaning or topic, or in the way they're used. So here we have three topics related to the outdoors: an ocean topic, a camping topic, a mountain topic. The size of the word corresponds to its prevalence within the topic. Another example of topics was produced using latent Dirichlet allocation over Facebook updates, and then we correlated it with gender. So here we have the top 6 topics most predictive of being female on the top left, and those most predictive of being male or self-identifying as those respective genders. And you see we get different clusters of words. This is helpful when one doesn't start out with a hypothesis to begin with and they just want to see what emerges, what is most prevalent. And you can see things like people who self-identify as women tend to talk about being excited more often, whereas people who self-identify as being men tend to talk about football more often, or government. You even can get nuanced differences, such as more of a freedom topic related to government, and then more of an economy or economic topic related to government. Lastly, there's words and phrases. These are just simply individual words or strings of words. Here we've got up to 3 grams, which are 3 words in a row, and looking at how they correlate. In this case, it's with extroversion. So all of these features are just examples. There's plenty of other features you could extract from language, such as part of speech tags, how often people are mentioning nouns, verbs, adjectives, or you could extract the syntactic structure or the grammatical relationships between words. What is the subject, the object? All of these features would lie somewhere along the continuum from the hand-driven to the data-driven. So when would you want to use something that's more on the hand-driven or the closed vocabulary side versus when would you want to use something that's open vocabulary that's not using any or using less manual judgments? Well, on the closed vocabulary side, the primary advantage is simplicity. Anyone can create a list of words. And usually these lists are a manageable number of variables ranging from 10 or maybe 50, at most 100 different categories of language that you break things into. This makes it quick to test a pre-existing hypothesis. If I wanted to test for how optimistic a given set of languages, I could create that lexicon using my knowledge or some of my colleagues' knowledge, and quickly be able to run that lexicon to test how many optimistic words are people using. It's also less domain dependent. That means when you create these lexica, they usually are applicable to multiple different domains. When you're using an open vocabulary approach, if it was designed over Facebook, it may not hold up quite as well, for example, if you ran it in the New York Times. Now, on the other hand, an open vocabulary approach makes few assumptions. Ambiguous words can be automatically filtered out. If you're working with a lexicon, for example, that positive emotions, you might not realize it, but words which are not actually expressing positive emotion might be driving the signals you're getting. So, for example, play would not emerge in an open vocabulary approach as being correlated or predictive of an outcome. Because you're looking at the data in more of its natural habitat, and if play isn't occurring often enough in a positive context, it's not going to get a positive score based on the statistics you use. It also has the advantage of finding patterns that are not hypothesized. For example, when we looked at conscientious individual language, we saw that they talk about relaxation and vacations. This wasn't something we hypothesized when we started that. It also usually yields the best results for prediction type tasks, for measurement. And that's because it's taking advantage of really the whole complete picture of the language. Any word or phrase that's used, usually you might apply a frequency filter. It has to be used at least a certain amount of time. But besides that, anything can emerge, and therefore you're capturing usually the maximal amount of variance. Now, in both cases, whether open vocabulary or closed, or even if you're using a combination of the two, which is also quite commonly done, you need to validate your model. So just because for example, if you've developed your model on Facebook, and when you apply it to a new domain, you need to test how well it works. Or maybe you've developed your lexicon without really looking at how people use words. You need to test how well your lexicon measures real-world uses of words. One of the more common ways to do this is to take a random set of, for example, tweets and have somebody annotate them. It's important this random set of data is from the same domain that you're applying your models to, and then you can see, well, what's the accuracy as compared to human judgments of a whole phrase. It's important when you're doing this validation that you look at words in their context, whole phrases, or whole tweets, or whole status updates, or whole documents if available. So we've talked a lot about the linguistic feature extraction, which is really where the open vocabulary distinction comes in. It depends on the type of feature you're extracting. However, we've been assuming you're mostly working with person-level data, and there's many other levels of analysis you could look at when doing language analysis over social science, or for social science. For example, usually the most basic layer is an individual message, or a tweet, or a status update, which is usually written by people. And people are often in communities, and communities are often in countries. And it's important to note that you could extract these features across any different level of analysis. Finally, let's talk about the statistical analyses you can run over these language as compared to your outcomes. Generally, you can break the statistical analyses down into two types: prediction and insight. In prediction, again, we're concerned with measuring a given outcome. And in this case, usually the types of approaches you would take are based on supervised machine learning, at least if you want to get the most accuracy out of your models. And this is where you see approaches like penalized linear regression, support vector machines, random forests, naive Bayes classifiers. These are a lot of techniques that are used in supervised machine learning where you're essentially fitting lots of variables to one or just a few given outcomes. For example, fitting tens of thousands of words and phrases to how extroverted somebody is. Now, there's whole courses on supervised machine learning, and there's plenty of great examples online. Certainly, it's a much deeper subject than we could get into in this tutorial, and I would encourage anyone interested in that side to pursue some of the tutorials available online. Now let's talk about insight, which is generally concerned with characterizing an outcome based on the language one uses. In this case, you might think, well, we could use one of the predictive models and just look at the weights that it learns. And so here's some weights across words predictive and a predictive model of gender. So on the top are words weighted towards the female side, and on the bottom words weighted toward the male side. So for example, blueberry was found as the second most highly weighted female word, and haircut is the third most highly weighted male word. Now, these types of models consider a bunch of variables at once and try to produce a prediction from all those variables, some of which tend to co-occur with each other or co-vary with each other a lot. If, on the other hand, you were to just consider all of those 10,000 variables one at a time and look at their correlation, controlled for age with gender, this is what you would get. So those self-reporting as female, actually the most predictive word for them is the less than 3 or the heart emoticon, and we don't even see the word blueberry in their top 100 words, which is what this is represented in this cloud. Similarly, haircut is not one of the top words predictive of being male on the other side. So why does this happen? When you're using a multivariate model, or a lot of the machine learning models, they have to deal with a lot of covariance between variables, and they tend to downweight words that occur with other words commonly. So blueberry might be getting such a high weight here because it's actually more of a unique word. And similar with haircut. There's other considerations too. They use large margin optimization. Basically, it would be very complicated to understand what the difference in weights means between each word. So for insight, you want to do things that are actually much more simpler, just at a larger scale. So instead of running 10 Pearson correlations, you can run 10,000 and make sure you correct for multiple tests. Any of your standard analyses can be used as long as you're not violating any of their assumptions: ordinary least squares linear regression, logistic regression, hierarchical linear models. And so here's an example of if you were running a linear regression and you wanted to find the words that correlate with conscientiousness, controlled for age and gender. Again, we're really just using each variable, each word, as if it's a variable. And so here, word represents the usage of a given word, and age represents the person's age, and gender the gender. And if you were to standardize these variables and run ordinary least squares linear regression, the beta 1 coefficient you would get for the word would be its correlation adjusted for the effect of age and gender with conscientiousness. So once you get your language down to the level where it becomes a variable, you can work with it in your standard statistical packages. Now it is important on the inside again that you correct for significance tests, for multiple tests. If you're looking at 20,000 words, well, that's close to probably 20,000 hypotheses you're testing. And these types of tests range from the Bonferroni, which is a little bit of an overcorrection, and the Benjamini-Hochberg false discovery rate is a little less strenuous test, but it's important those are tried because, yeah, if you're looking at 20,000 words and you're using a p-value of 0.05 to test significance, then, well, 5% of those 20,000 words are just by chance likely to be significant. So this concludes the tutorial today. Please feel free to email us if you have any questions. If you have something more specific, you can email me directly at andrewschwartz@cs.stonybrook.edu. Thank you.